In this video, we will discuss the tangent and velocity problems. We have three learning objectives. First, know the definition for what a secant and tangent line is. Second, be able to calculate average and instantaneous velocities, or at least an approximation for an instantaneous velocity. And the third is to find the equations for tangent and secant lines. Vocabulary, of course, you can see at the bottom. We'll get started. First of all, we have these two graphs. It's a lot easier to use a picture to develop an understanding for tangent and secant instead of the verbiage. So, short version, this is a secant line. And that's a secant line. Secant lines cut across a shape. So they're intersecting at like 2 points. You'll note, though, if we start dragging the shape out, or dragging the line across the shape, we still have 2 points of intersection, so it's still a secant line. You drag it too far, and they're not intersecting at all. Well, there is a point where you go from 2 intersections until you get to be exactly 1. At this point, you can almost think of it as like a little ricochet, where it's just barely glancing off the surface and kind of skipping forward, staying on its same path, the same trajectory, just barely glances it. This one on the right would have right about there, where you can see they just barely touch each other. If you have it so that it's just barely touching like this, that's when it's called a tangent line. And of course, this line could be tangent at the bottom. It could be tangent up here at the top. But I would like to point out, if you had something like this, how it actually cuts across. That's not a tangent line, because going through it is not the same thing as glancing off it. Continuing. Our first example is find an equation of the tangent line to the parabola at the point -1, 1. Well, since we're being asked to find the equation of a line, it makes sense that we should quickly review the equation for a line. You should remember that if we had point-slope form of a line, that can be written y minus y1 equals m x minus x1. And here's where we are going to start. We could take a line, and I want to switch this to blue. I could take a line and just say, all right, I'm cutting across. Hooray, I have a line. And I could go through and figure out, say, okay, I have 2 points. From those 2 points, I can figure out rise and run to get my slope, and I could use one of those points to get the equation. But specifically, we were asked to find the equation of the line tangent to the parabola at this point, -1, 1. So at that point, we should have it come and glance just barely off. Okay, and that's not quite right. Oh, sorry. But something like this, where it just barely touches it and keeps going. This would be the tangent line. Well, we do know it is intersecting at this 1 point. That's the whole reason why we're doing this. And so we could take this point and plug it into the point-slope form we have written in the black to get y minus 1. I started writing +1, so please let me fix that. Y minus 1 equals the slope x plus 1. Because, of course, subtracting a negative is adding a positive. And the only thing that we have left to do is to figure out what is the slope of that line. But here's the problem. We only have 1 point. And it's not like I can go through and say, whoa, check it out, I've got this other point here, because we don't know where this piece is. I just did a quick sketch for this piece in the blue. We only have one point. So what could we possibly do then? We know that if you want to calculate slope, the general formula is to take like y2 minus y1 over x2 minus x1. That's just our simple rise over run. But we only have these 2 points. This is why when I'd mentioned our learning objectives, when we're looking at calculating an instantaneous velocity and finding equations for tangent lines, with those problems, we are going to be doing approximations for right now. With increased technique, we will actually be able to calculate them exactly, but with our current skill set, with our current toolbox, we can't do it yet, but we will. The idea, though, is still fairly straightforward. We have this line, and if I were going to say, use another line that's close to it, like right here. Oh, sorry, I want to get this straighter. If I were to pick this line right here, this would be a secant line that does go pretty close to this one. What do you think about the slopes for the red and the blue, though? Are they pretty close to each other? No, so I wouldn't want to use that one. But I could say, perhaps take this one and say, hey, that's pretty dang close. Remember that when we are doing these pieces, that this tangent line could have come by taking a secant line and actually dragging it to the point where it comes out and is right there. So what we're trying to do then is say, what about here? Instead of using that, we would have 2 points right here and right here that are actually on the line. Those would be 2 points that would be very good to be able to use, because the slopes are going to be about the same, but getting equations for those is going to be a little bit tricky, because we'd like this to get as close as we possibly can. Yes, we could pick a line that's like out here. I'm sorry, let me switch the colors. I could pick a line that's all the way like out here, and it doesn't work very well. But if I start taking a line that goes through this point and over to this x coordinate, if I start switching it over so that it's closer and then closer, you can see that the closer that this gets to be the matching x coordinates, the closer the slope is getting. That's the big idea behind what we're trying to do. We could take the secant line through a point right here and right there and say that line has slope that's really, 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 really close. The closer we could get these points wrapping around, the better off we will be. So what I mean by this is, for our x2 and x1, we could use a piece that's wrapping around the -1. We could use, say, -1.1 for 1 point, and we could use -0.9. The two numbers that are a little bit to the left and a little bit to the right. This is one way that we can do it. Well, we know the equation of this line because it's the parabola. We know the parabola is y equals x squared. So we could actually go through and plug in 1.1 squared, -0.9 squared, and just by crunching these numbers, we can get the y values that will then match up. But the closer we can get these things to what's actually the actual value that we want, the better we will be. We could use 1.1 and we could use 0.9. But 0.99 is closer. 0.999 is even closer still. The more of these 9s that we start adding, the closer to what we will actually have will be. But frankly, using that many 9s just starts getting more and more and more tedious. It's pretty easy just to go through and say, let's do 3, and we'll do all the number crunching with the calculator. Same piece here. Instead of going 1.1, we can go 1.001. And these are pieces that are very, very, very close. So, putting them in to get our y values that go with it, I'm going to come and use this calculator. And we'll take 1.001 squared equals 1.002001. So 1.002001. And we'll do the same piece when we take 0.999 squared. 0.999 squared, 998001. 998001. And just by picking points that are a tiny little bit to the left and a tiny little bit to the right, we can actually get the slope of the secant line that's really, really, really close to being tangent. Just using these now, we would have y2, 1.002001, subtract 0.998001, which would equal 0.004. Taking x2 minus x1, we'd have negative 1.001 subtract a negative 0.999. That's x2, x1. Yeah. That winds up giving us 1.001 negative, subtract 0.999 negative. Oh, back this part up. Subtract negative. Oh, okay. I'm learning the programming of the calculator. Well, subtracting a negative is taking plus a positive, so plus 0.999. We'll see 0.002. Negative 0.002, which is 1/500th. Should just skip to that right away, not bothered with the calculator, but 0.002. When we divide that out, we get 2. So the slope of that secant line is 2. But since that's ridiculously close to the blue one, what do you suppose the slope of the blue line is? Probably the same thing. And so there we go. We have an estimate for the slope of the tangent line at that point. It was based on the idea that we could get the slope of a secant line of something really, really close to the tangent. Where would we possibly do this thing? Basically, we did this problem where we got a tangent line and we've estimated the slope of a tangent, and we look at it and say, why do we give a crap? Why would we want to know about tangent lines? Well, tangent lines actually have a tremendous amount of applications. Here's one of them. The flash bulb on a camera operates by storing an electrical charge on a capacitor, and then it releases that electrical charge suddenly when the flash is set off. The data in the table describes the charge Q, which is measured in microcoulombs, and time, T, which is measured in seconds after the flash goes off. So let me start by labeling my axes. I have Q, we have T, and Q goes up to 100, so we'll say 100, 90, 80, 70, 60, 50, 40, 30, 20. Okay, my spacing's bad. So 50, there's 100, there's 50, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So 100, 80, 60, 50, whoa, 40, not 50, 20, 0. And time goes from 0 seconds to 0.1, so here's 0.1, say 0.5, so 0.1, 0.0, 1, 2, 3, 4. Man, my spacing is just all messed up today. 1, 2, 3, 4, 5, 6, 7, 8, 9. So here's 0.02, 0.04, 0.06, 0.08, 0.10. Okay, finally got them in. Sorry it took so long. Use the data to draw the graph of this function and estimate the slope of the tangent line at the point where t equals 0.06. Okay, so we got to plot the points. T of 0 corresponds to 100. T of 0.02 is about 82, so 82. 0.04 is 67, so we'll go up to 60, a little bit below. And then we have about 55, so 40, 50, halfway. 0.08 would be 45. So there's 40, 45. 0.10 is about 37, 20, 37. And so we wind up with this. Please note, we do not have an equation on this. In the last problem, we had the equation for the parabola. In this one, we don't. So when we go through and say, okay, well, hooray, we've got this line, or we have this graph, and we want the equation for the tangent line, or specifically, we want the slope of the tangent line. At 0.06, that's saying right here, what is the slope of that line? We need to have an estimate for it. And the big problem that we have is we don't have an equation. In the last problem, we used the equation to start crunching these numbers. We don't have that now. So we're at a bit of a disadvantage. Well, here are some possibilities. We could use a graphing calculator, and we could type in all this information into the lists, and we could do a linear regression for it. Or not a linear regression, because this is fairly evident. It's pretty clear that this is not actually a line. This looks like an exponential graph. And so we could do an exponential regression, which would allow us to create an equation that won't be perfect, but it's the best model that we would be able to create. And then we could go through and do that. Absolutely valid strategy, completely fine. But we are actually going to use this graph. We know that we could take points that are just a tiny little bit on either side. Not by a whole lot. So let's go through and say this piece. We are concerned at 0.06. One estimate that is admittedly not going to be perfect, but we could take 0.05, and 0.05 we would expect to be maybe about halfway between 0.4 and 0.6. So if we went halfway between 67 and 54, that would give us, see, 67 and 54 are 13 apart. If we just average those two out, let's grab a calculator and do that. 67.03 plus, 67.03 plus, and then the other one we had was 54.88 equals, and when we divide that in half, we get an estimate of 60.955, which we could then say, okay, 60.96 when we round it. That would give us 1 point that we could use. We could also go through and do the same component for 0.06 and 0.08 to get an estimate for 0.07. That one would be 44.93 44.93 plus 54.88 and divide them in half, and we get an estimate of 49.91. So it's 49.91. Yeah, 49.91. And so there we go. We could use some linear interpolation to get an idea and get 2 points, which we could then use to say 60.96 subtract 49.91, which would give us 11.05 over 0.02. Well, that 0.02 I had from 0.05 minus 0.07, so negative 0.02. And when we take that, that would be 1,105 over 2, negative 2, so that's negative 552.5. And so there we go. We have an estimate for slope. Negative 552.5 microcoulombs per second. But that's still like, we have this estimate, but is it the best possible estimate we could have done? Picking pieces like 0.05 and 0.07, yes, they're 100th of a second off in either way, but when we're measuring down to 0.06, that seems to be almost like it would be too far away. Nonetheless, it's the best that we can do. If we would like to get a better estimate, we could go through and actually create a regression model, use the equation from the regression model, and instead of doing pieces like 0.05, 0.07, with the equation from the regression model, we could actually go through and do 0.0599 and 0.0601. Using a more precise and close times, as well as the microcoulomb level that go along with them, would give us a better estimate. But we would need to do the regression, and we do not have the time to go through and do that full process. Did you notice the note in the last problem? Written right here. I didn't take the time to read it. But the slope represents the electric current that flows from the capacitor to the flash bulb. That's an example of a velocity problem. That problem was talking about how fast can the capacitor send the electric to the bulb. If you think about cameras, think about your phone camera. It has the flash on it. When you press to take a photo, how long does it take to actually take the picture? There is an amount of time where it brings up the flash, and then it has that brief moment. If you actually had to design a camera, the better camera you can make, the more you'd be able to sell it, because people don't want to buy crap. They want to buy something of quality. So if you're working on building a camera, you want to have something that has a very fast shutter speed, so you can take pictures very, very quickly, and you want to be able to take good pictures very, very quickly. Well, you could sit and mess around and say, well, we've got this piece, well, let's do trial and error, and I'm going to change how fast this capacitor sends electricity, and then we're going to go check out the camera and see how well it works. That's a bad technique, because if you have to spend all the time in building a new capacitor every time you want to try one tiny little thing that's different, it's a huge waste of time, it's a waste of money, because it takes time to build and it costs money to build. But you could use this type of a problem and say, which is the best one? When you are doing pieces like regression, you could say, mathematics tells us this is the best possible choice we can have, and you don't need to go through 20 different prototypes. You can just say, this is the one that mathematically is best. So Just build the one. Build one model, save time, save money, and then be able to have the best camera that you know how to build. Those types of problems, though, are based on a velocity piece. The faster that you can have the capacitor releasing, the better our camera you'll make. That's a velocity problem. In calculus, velocity problems are absolutely critical. You do all kinds of things that are based on speed. And especially when you talk about how speed changes. Easiest example you could think of is your car. You look at the speedometer on your car and you don't constantly drive 75 miles per hour every single second. You don't constantly maintain a speed of 50 kilometers per hour every single second. Your speed is going to go up, your speed will go down. But one of the things that's kind of important about it is you don't want your speedometer to say, well, 5 miles ago you were driving 70. Your speedometer is indicating right now this is how fast you're driving. Right now this is your speed. And that concept of right now is what's going to be important for us. Yes, we can get a really, really close approximation by using a secant line. But even this secant line that we did in the capacitor problem and the secant line we did in this parabola problem, they are not what's going on right now instantly. They are what happened over this tiny little period of time. Yeah, a tiny little period of time for 0.002 or 0.02. 1/50th of a second or 1/500th of a second may not seem like it's that big of a deal, but it's still not right now. The secant lines that we were doing were actually average velocity problems. They are what the speed was over a period of time. Now again, that time was really, really small with 0.02 seconds, or really, really small with a 50th of a second, a 500th of a second. And if we wanted to add on more nines, we could have turned it into something that's even smaller and done like a 10,000th or 100,000th of a second. We can make that distance really, really small. But no matter how small you make it, it's still not right now. Instantaneous velocity is that. So here, suppose you drop a coin off the top of the Empire State Building in New York City. How fast will the coin be falling 4 seconds after you drop it? Here are some hints for you. The Empire State Building is 443 meters tall. And Galileo proved centuries ago that the distance, the total distance, not the speed, the distance traveled by a falling object is governed by this equation. D of t equals 4.9 t squared, where t is measured in seconds and d is measured in meters. So here's the big thing. How fast is it going? We don't have an equation here that says this is the speed. We have an equation that says this is the distance. Well, fortunately for us, we can go distance, we know is rate multiplied by time. So if we want the rate, we just have to take distance divided by time to get the speed. All right, so let's start here. At a time of 4, we had, well, let's start here. At a time of 1 second, we'd have 4.9 times 1 squared. And 4.9 times 1 squared is 4.9. That tells us if you drop an object after 1 second, it will have fallen 4.9 meters. If we wait 2 seconds, that will be 4.9 times 2 squared. 4.9 times 2 squared is 4.9 times 4. And 4.9 times 4 equals 19.6. So in 2 seconds, it will have fallen 19.6 meters. At 3 seconds, we'd have 4.9 times 3 squared, and 4.9 times 9 is 44.1 meters. D of 4, that's 4.9 times 4 squared, and 4.9 times 16 is 78.4. Okay, so hooray, we're at this point. After 4 seconds, it has fallen a total of 78.4. Well, we could use those and say distance was 78.4, the time was 4 seconds, and so the speed then, 78.4 divided by 4 equals 19.6. Do you actually think it was falling at a rate of 19.6 meters per second? Because it wasn't. This piece that I just calculated, this was based on a time interval of 4 seconds. From the time of 0 until the time of 4 seconds, the average speed was 19.6. Is that the best estimate we could do? Well, let's say if we go from 3 seconds to 4 seconds. Let's check those numbers. Okay, from 3 seconds to 4 seconds, how far did it fall? 78.4 minus 44.1 over 4 subtract 3, which would of course be 1. So 78.4 minus 44.1 gives us 34.3 over 1. And so at that point, it's saying it was falling at a speed between 3 seconds and 4 seconds. It was falling at a speed of 34.3 meters per second. You notice how it's picking up the speed? When you first drop an object, yes, it will start to fall, but it's not falling very fast. The longer it falls, the more speed it will pick up. Of course, if it runs out of room by hitting the ground, that's going to make it stop pretty quickly. Wind resistance would actually play a factor, and that's not included with this particular equation. But basically, we're looking at this piece and saying, yes, it's a nice estimate, but is it really the best one? We went from 3 to 4, but if you want to have a more precise one, you need to make sure that this interval is as small as you possibly can get it, as small as practical. And so we don't want to be going from 3 seconds to 4 seconds. We'd like to be going from, say, 3.99 seconds and 4.01 seconds, because that's a very, very small window. When we start using those, we'd have 4.9 times 3.99 squared. And I'm using a calculator to help crunch those numbers. We get 78.00849. Doing the same thing here. 4.9 times 4.01 squared gives me 78.79249. And you can see, even over this tiny little window of only 0.02 of a second, we can see that it's already speeding up and traveling even bigger distances. So to get the speed, we'd have 78.79249 subtract 78.00849 all over. This one was 4.01 subtract 3.99. When we simplify those, 792 minus 8, that's 0.784 over 0.02, which is 78.4 over 2, and that is equal to 39.2. Even over this tiny little distance, That's its current speed. 39.2 meters per second is how fast it's falling. And we know that is still changing. It's still speeding up. That's a lot better estimate than we'd initially started off and said. Over from 0 to 4, our first answer was 19.6. That was a very bad estimate because it was over such a wide period of time. Over a smaller period of time of only 1 second, we got a closer answer. But when we switched down to even smaller of a 0.02, we got an even better answer. You notice, for those of you who had taken pre-calculus, do you notice the limit process that's going on here? The limit, as this time gets smaller and smaller and smaller, from 4 to 1 to 1/50th, and if we kept going to like a millionth, a 100 billionth, that's where we will use the limits that you had practiced in pre-calculus. If we want to know the instantaneous, right now velocity, we will need to do limits that you'd studied in your previous courses. That's where we're going with this piece. We're going to combine the limits that you learned before with the tangent and slope information that you did before, and that's a significant part of calculus. We will be able to use those to solve a lot of pieces with tangents and velocities. Tangent and velocity problems are all about slope of a line, but it's slope of a tangent line. Please remember our learning objectives for today. Do you know what a tangent line is? Do you know what a secant line is? Do you have a mental image of what they look like? Would you be able to calculate average velocity over a period of time and use that to estimate the instantaneous velocity? Remember, when you're talking about average and instantaneous velocities, those are slopes. Slopes you would use to create the equations for your tangent and secant lines. They all flow together. A number of problems that we'd be able to adapt with them. Make sure you know what the secant. You got to know how to do slope. You got to know how to build the equations.